All right, hello mathematicians. We're going to look at section 7.3 in this lecture broadcasting live from my office in Cedar Grove, New Jersey. We're going to look at anti-differentiation by parts or integration by parts. So if you're following along in your packet, I'm going to start right with this page. I'm going to show you the integration by parts formula, and then we're going to derive it, and I'll give a little background of the method. So the formula says the integral of u dv is equal to the product of u times v minus the integral of v du. Now, what are these u's and v's? So I'll also add, this is where u and v are functions. U and v are some given functions in the problem. One way, because you are going to have to memorize this formula as a technique for integrating certain functions. One way to remember this, a lot of people say integration by parts is voodoo, VDU. The VDU can be confused with the UDV. So people say, okay, it's UV minus voodoo, and that's how they remember that. In a college course like analysis, you would prove the integration by parts formula. But that's not required in AP high school calculus. So we're simply going to use it to calculate various integrals. I'll give you a little derivation, though, of where this comes from. This is a bit informal, but enough to make the point. So let's look at some background of the method. This method actually comes from the product rule of taking derivatives. So say we wanted to take the derivative of u times v with respect to x. If we apply the product rule here, this would be u times first times the derivative of the second, which would be 1 and then v prime, because this is implicit differentiation. So it would be u times dv dx plus, and then second times derivative of first, that would be v times 1 times du dx. Since we need the chain rule there as we integrate implicitly. Okay, next we're going to rearrange some terms here. And I'm going to bring the v times du dx. I'm going to subtract that from both sides, and I'm just going to rewrite this with the u times dv dx on the left-hand side. So here's what we have. U times dv dx equals, and then we have ddx of uv minus, and then we subtracted this, so this will be v times du dx. All right, excuse my handwriting here. It does take me a little while. A little tricky to type those with the mouse, but that's where we're at. The next step in our derivation is we're actually going to integrate both sides, term by term, with respect to x. So each term, I'm going to surround with an integral. Let's see if I can do a different color here. Let's try that. So the first integral, and these are all going to be dx integrals. I'm going to put this thing inside of it, and then we'll have an equal sign. We're integrating both sides. The second integral, I'm going to put this thing inside of it. And then the third integral, we have minus, I'm going to put this term inside of that. These are all going to be dx integrals. We're integrating both sides with respect to x. And let's see what happens when we do that. Okay, so let's put that first term in, u times dv dx. The next term is, we have uv, I'm going to write it like this. I'm sorry. It's ddx and then uv. And then the last term, which is v times du dx. As you can see, if we treat these little dx's as if they're little quantities, we have some cancellations that emerge. And this is how we can complete the mini proof, or the informal proof, we could say, of our integration by parts formula. Here, the dx's cancel out. Here, the integral of the derivative, by the fundamental theorem of calculus, the integral of a derivative, well, those things cancel each other out. So these cancel out, and we just end up with the function, uv. And then here, these dx's cancel out, and you'll notice what's left that I circle in blue is our integration by parts formula. We have u dv, and then we have uv, and then we have minus the integral of v du. So that's where the formula comes from, and then we're going to use it to integrate various functions. A couple quick tips here, and I'm going to type these so it'll go a little faster. Okay, so I just typed in 3 bullet points here with some important tips of how we're going to use the integration by parts formula. And then in the next video, we're going to look at 3 examples together. So first, with a proper choice of u and v, the second integral is easier to calculate or evaluate. If you make the wrong choice, you're going to choose something to be your v, something to be your u, something to be your dv. And if you make the wrong choices, this integral ends up being too difficult to evaluate. We just can't do it analytically. In general, when you make your pick, u should be a function that differentiates to 0. For example, any polynomial, like x to the 5th, that would differentiate to 0 eventually when you keep taking derivatives. But a function like e to the x would not be a good choice, because you could take the derivative over and over and it's still e to the x. dv, which I'm going to show you in a second in an example what it looks like when we choose these, but dv should contain a function we can integrate analytically. And with these 3 tips in mind and the formula, we're going to proceed to several examples. Thanks for watching this short video on the background of integration by parts.